optimized Genesis sequence.
Hello, welcome. This is a talk about Project Loom. This is the last session of the conference, so it's actually nice that we actually have some people here and they haven't been running away for trains or planes. Before I start, can I just get a quick show of hands as to how many people have actually or already have some familiarity with virtual threads? Maybe you've tried them? Okay, so a good show of hands. So for the people that did show hands, how many people actually know what the word pinning means? How many people have experienced it? Some show of hands. Okay, so this project has introduced two interesting words to the industry. So there was a lot of user mode threads in the industry for a long time. Green threads were what people called things for a long time. Brian came up with the word virtual threads because it's a bit like threading it for, a bit like virtual memory, but for threads. So that's where virtual threads. So we ended up introducing a nice, good term, but a bad term, pinning, has actually come into the vocabulary of developers in the meantime. So we will try to address that one in this session. Okay, so for those that haven't really familiar with what Project Loom and virtual threads are all about, I'll just quickly in 30 seconds try and go through what it's all about. So the overall objective of this project in OpenJDK has been about enabling really increasing concurrency, high-scale server applications. And the main concept that we've introduced, or the main thing that we've introduced is virtual threads. There's a number of other things that I'll be talking about today, but virtual threads are basically these lightweight or user mode threads that actually they run a single task. So we've been in the Java ecosystem have been used to threads being quite an expensive resource over the last 25 years. We're used to actually sharing them. We've been used to actually using thread pools. With virtual threads, we go back to a world of thread per request, thread per task, thread per connection. Very, very simple programming model. We can have 1 million plus virtual threads in a single virtual machine. We can have a million plus connections where each connection or network connection is managed by a single virtual thread. So that's actually very, very cool. But doing this, we're essentially introducing a different implementation of Java Lang thread. We have not introduced any new API. Yes, there's some little APIs to be able to actually create these virtual threads, but for the most part, existing APIs, existing thread API, everything that actually assumes a thread of execution is able to run with these virtual threads. And the big benefit is that you end up with by having the thread per request type model, is you can write basic, boring, simple blocking synchronous code that's easy to read, it's easy to debug, and so on. And what it means is that we don't have to be tempted to go down the road of writing contorted code with reactive or async type of model. So that's actually the big benefit of virtual threads. So as a feature, this feature became a permanent feature in JDK 21. We had it in preview for 2 releases before that, so a lot of people actually jumped on it in that time, and they were ready with their libraries and their frameworks when it became permanent in 21. So in general, I think the feedback is it's been very well received by the ecosystem. There's been a lot of excitement around it. A lot of excitement is almost at the scale of the excitement that was with streams and lambdas back in JDK 8. And what's interesting about it is that people are actually really interested in going back to simple blocking synchronous code, the boring code, which is maybe not where people wanted to go a few years ago. Most of the frameworks, most of the web app servers, they all have something for virtual threads today, either as an opt-in, or in some of them they've actually added new APIs for this as well. Overall, after a year of it being in JDK 21, what I can say is the performance is actually looking quite good. The reliability has been quite good. There's been very, very few bug reports. Now, there has been some pain points. I'm going to talk about one of those big pain points today. But for the most part, it actually has been working quite well. So there's a couple of other features going on in Project Loom. I've just listed 2 of them here, and I'm going to be talking quite a bit about one of them today. So under the banner of actually grouping threads. So if you have a lot of threads, high concurrency, you want to think about how you're actually going to manage and group those threads. So I'll be talking about structured concurrency today. Once you start having lots of threads that are actually very short-lived and existing only for the lifetime of a task, then you get into some of the challenges around using thread locals. So a number of explorations into that, and one of the things that we've had in preview for a couple of releases now is scope values. I'm not going to go into that today. We spent a lot of time on this at DevOps last year, and maybe in the future more presentations on this, but that's a better alternative for than thread locals for certain use cases. So next steps in Project Loom. So there's a lot of things going on. I'm going to focus today on three things. One of them is the pinning issue, which is related to the synchronized keyword, synchronized methods, and some of the challenges, implementations issues there that are causing scalability problems. I want to talk about serviceability and some of the troubleshooting, because as applications are deployed in production with a large number of virtual threads, you end up with interesting scenarios. How am I going to debug them? How am I actually going to see what's actually going on? What is the VM going to give me an insight into? And I want to talk today then about structured concurrency, because we need to make progress over the next year or two and over the couple of releases on these two features. Okay, so before I go into some of the detail on this, I just wanted to actually just have this important slide, because a lot of people have been excited about virtual threads, but I need to make it very, very clear that virtual threads are not pixie dust. There are people, and Ron Pressler, who's been leading this project, and myself, we've been reading a lot of blogs and articles and other things that people have actually written, and it's clear that some people are actually making mistakes. So what I've put down on the slide here are just things that we have noticed by reading some of these things where people don't quite have the right mindset in this. So sometimes you read articles and you get the perception that somehow virtual threads are faster. They make my code go faster than a platform thread. That's not the case. They don't make a method go faster than it did on a platform thread. It's the same code. They'll execute at the same time. What we've noticed is some people are running into the trap of actually just replacing. Well, I've got this X number of threads here. I'm just going to replace all of those threads with virtual threads, and I'm done. And that doesn't really. That's not really what. It's not about replacing platform threads with virtual threads. When you're migrating existing systems, it's about migrating the task to a virtual thread, not the platform thread to a virtual thread. So important to keep that in mind. We see people actually replacing their thread factory. Oh, my whole server is actually configured with this with thread factory that creates my threads, and they're changing that just to create virtual threads, and they end up creating a thread pool with virtual threads. And virtual threads were never intended to be pooled. They're not for pooling. They're very, very cheap. You create one for a task, executes the task, and it's done. Thread terminates. So the pinning issues, which I'm going to talk a little bit about today, is something that there are literally hundreds of articles. Every single conference over the last year has had somebody talking about their experiences with this issue. And one of the things I've noticed is that people writing up their after listening to these is they make the assumption that the synchronized keyword doesn't work with virtual threads. And that's actually not true. It's that there's a quality of implementation issue that I will get into. There's no need to be replacing the synchronized keyword or synchronized methods for many types of usages. Thread locals are a challenge because a lot of libraries out there are making the assumption that their threads are pooled. There's people that are doing kind of overly complicated stuff with virtual threads, and there's no need to do any of this. You actually write very simple synchronous code. So what I would say is that sometimes there's a kind of a misunderstanding as to where the advantages of virtual threads come from. And the advantage comes from one thing, their number. You can have lots of them, really, really lots of them. Okay, that's I've got off my soapbox now, and I'll move on to the rest of the talk. So three topics I want to get through today. First one is pinning. I just want to quickly go through what we're doing on this one. So very, very quickly, how do virtual threads actually work? Well, in terms of threading models, it's an end-to-end threading model. You've got a large number of virtual threads that actually execute over a small number of platform threads. It's conceptually quite simple. So what happens is, if I go and start a virtual thread to execute a method, in this particular example, it's just called toWork. I'm using an API here, thread start virtual thread, that's essentially the runnable. There's a Lambda there to run do work. What happens in terminology? We say that the virtual thread is mounted on one of these platform threads or carrier threads, as it's called. It executes this method, and then when the method is done, and this is the end, the thread is going to terminate, it unmounts from its carrier. So the terminology that we actually use is mount and unmount when you're actually executing code. I'll show you an example here where we run a blocking operation. This is actually using a semaphore. A semaphore has two operations, an acquire and release. The acquire method gives you a permit. If there's no permit available, you actually block on the acquire method until there's a permit available. A virtual thread executing this is initially mounted, it gets to the acquire, there's no permits available, so it actually has to block. What happens when it blocks? It unmounts from its carrier thread, which makes that thread available to go and do other work. When a permit is available, the virtual thread can execute again, so it's remounted on a carrier, maybe a different carrier than previously, and it continues execution. So we're here we have mounting and unmounting. Here we have another operation. This one is doing an I/O operation on a socket. So I'm doing a socket get input stream read. This is actually reads bytes from a socket. If there's no bytes available, this is going to block. What we do, we unmount the virtual thread, and that releases the underlying carrier to go and do other work. When there's bytes available and the thread can continue, it'll get remounted onto some other carrier thread and actually continue. So it's mounted again. So this mounting and unmounting that's going on, it happens transparently. It happens very frequently. You have no control as to whether it actually it's done. But this is what's actually going on behind the scenes. Now in JEP 4.4.4. we have a few little caveats for when this doesn't quite work. And with two of them we've actually listed here. I'm going to focus on one of them, which is when it executes code inside a synchronized method, block or method. Okay, what does it mean by inside? I'll go through these cases here. So here we have a synchronized method. So I've put the synchronized keyword on my do work method, and I've taken the socket read that was in the previous example, and I've put it inside the method. If I were to block at this point, I cannot release the carrier to do other work. I cannot unmount. That is an implementation, quality of implementation issue that I want to get into. So if I can't unmount at this point, it means I can't release the underlying thread to do other work. So I've got a scalability issue. Sad face. Now we have another example here where the synchronized keyword is all about mutual exclusion. If there's some other thread executing inside of do work, and then I want to go and call it, I have to block because some other thread is executing inside. Only one thread can be inside at the same time. This is another example where I cannot release the carrier, I cannot unmount. So scalability issue here, sad face. Third scenario with object monitors is object wait. So for those who are familiar with the synchronized keyword, you can use object wait and notify for more complicated use of monitors. And if I block in object wait, which means I'm waiting to be notified, then I'm also unable to unmount. So third sad face. Right, so let's go back to what we had, the text that we had in JEP 4.4.4, which is after the two caveats, we say pinning does not make an application incorrect, but it might hinder its scalability. We could have said more there, because it's not just scalability, it's potentially starvation, it's potentially deadlock. If all of these, if all of my carrier threads are actually are pinned by these virtual threads, they can't make progress, they can't execute other work, so my system might actually halt and deadlock. So some people have experienced this. A lot of people have actually written to us about this. So this has been a pain point that has been there from the beginning with virtual threads. Okay, so two other points I just want to bring up from JEP 4.4.4 is we put a statement in there is that for certain cases where you have long-lived operations where you block inside synchronized methods, then you can mechanically migrate that code from using object monitors and the synchronized keyword to using JavaUtil concurrent locks, reentrant lock. Okay, I can get this to work by modifying my code, but that's actually that's not a nice thing to have to go and execute, or sorry, to migrate my code in order to run in virtual threads. Hey, you've been selling me here for the last few years the possibility that all my existing code can actually run in the context of virtual thread. Now you're telling me that I have to go and migrate. So that's actually disappointing, but something that we put in there as a possible way to work around this issue. And this is where we lead to the next statement, which is you don't really have to go and replace all of your monitors. Anything that's actually just guarding memory, so you're just using mutual exclusion because you've got some mutable object, you're not blocking really inside that synchronized method. There's no need to migrate that code. However, that's a complicated story to tell people. You're saying, on one hand, I've got to go and replace my existing uses of monitors with JavaUtil concurrent locks, but over here, you're telling me that if I'm just using it for mutual exclusion and not doing blocking operations, I don't need to migrate my code. That's a complicated story, and it's hard to communicate. So, well, anyway, the good news is we're going to make this problem go away. So we have a JEP. It's JEP 491, synchronized virtual threads without pinning, that's currently on the technical roadmap that will address this issue. So this revisits the implementation of object monitors in the VM to be able to address the pain points that I've talked about. And in this JEP 491, what we have put a statement is it should not be necessary to abandon synchronized methods and statements in order to enjoy the scalability benefits of virtual threads. So what we want to do is address this issue so that you don't have to go and migrate code. It's embarrassing that you have to go and migrate code in order to get this to work. So what does this JEP give us? The implementation of this, it gives us the three things. It means that we can actually block inside of synchronized methods and release the carrier. It means that we can, if there's contention on a method because of some other thread executing, and we have to block, then we're able to release the carrier. Good. And then we've got object wait and notify, and they're also working with this as well. We can release the carrier. So this addresses the problem with object monitors. So this is a really, really important change to actually get in. So we have early access builds of this available. We did our first early access build of this in February of this year. This is quite a significant change to the VM. So we've actually gone through a couple of phases on this. And we're really, really hoping to be able to get this change into JDK 24. It will be really, really useful to get more people trying this out. And early access builds are something that you have to go out of your way and take time away from your job to be able to actually try these things out. But it's really, really important, given the invasive changes here, to be able to help us prove the reliability and the performance of this. And several people have, over the last few months, been reporting back success using these builds. So this is good. Okay, that's the end of pinning. Now I want to talk about troubleshooting. So if you're looking for trouble, this is the right session to come to. Okay, so when I talk about troubleshooting, I'm talking about things like stack traces, thread dumps. These are the things that we kind of assume that are there. And there's a whole bunch of other serviceability features that once you have even in development, not just production, you need to be able to actually diagnose why things are actually happening and what problems you might be actually having to figure out. So the platform and the JDK has been around for 30 years now, and there's a huge number of serviceability, observability, diagnosability, troubleshooting features that have built up in that time. A lot of them are actually assume platform threads, and it's not that we're starting again with virtual threads, but it gives us an opportunity to revisit what are the right features to be able to expose with virtual threads, to be able to diagnose those problems. So virtual threads, you get stack traces for free, of course. They're exactly the same as the stack traces that we get with platform threads. Really, really important thing to be able to see where something is coming from and seeing what method is in and so on. So what else do we have? So let me start going through a couple of things. There's a dozen different ways to be able to create a thread dump in the JDK. There's the JStack tool. You can use JCommand. There's control/, and there's a whole bunch of other ways to actually to do this thing. So one of the things that we have done, and it's there since the feature went into the JDK, is for diagnosability for diagnosability purposes. When you get a thread dump, it will tell you in the thread dump if that thread is being used to carry a virtual thread, and it gives you the thread identifier of the virtual thread, so you can actually see that something is being carried by this virtual thread. So that's useful to go and have. By the way, the color coding I'm using on this slide is deliberate, and you'll see that as we go forward. This dark blue here is representing our carrier thread. In JDK 24, which is currently our early access builds, this has been improved further to be able to include the stack trace of the mounted virtual thread. So I'm actually getting 2 stack traces in the thread dump, which is very, very useful for diagnostic purposes. So it's my traditional hotspot thread dump. Here's my carrier thread. I see its stack trace. I see all what it's doing, and then I also go and see the mounted virtual thread and what it's executing. So this is very, very useful. Next thing is we introduce as part of virtual threads, we introduce a completely new virtual thread that isn't saddled with the baggage of all of the other features that went with thread dumps in the past. This thread dump is created without actually having to go and do a safe pointing the VM. It's created in a different way. What it's doing is it's giving me a dump of all of the threads. When I say all, if you have 1 million virtual threads, you are going to see 1 million virtual threads in this output. And it can produce them in different formats, but the main thing is you can generate it in JSON format, which is parsable. When I was here 2 years ago, I think I showed a JavaX-based tool which actually did a visualizer to be able to actually to look at the threads, because it's parsable output, and that was actually very, very useful. Other things with this thread dump is that it actually has the thread groupings. If I have a thread pool in there, they're actually in a JSON array. I can actually see what those threads are. If I've organized my virtual threads into different type of groups, that structure is preserved in the thread dump, which is very, very useful to get. Okay, so for pinning issues, this is a couple of diagnostic features that are in there. There's one of them is a fairly ad hoc thing that we've had there since the beginning, which is a system property where you can actually just set it on the command line, and when you block inside inside a synchronized method, you get a stack trace printed. It's a very ad hoc type of a thing, but I know that people have actually found it useful for finding issues. So that is one thing that is there for diagnostic purposes. We have a better feature for diagnosing pinning issues, and that is in the form of a JFR event that gets recorded when you attempt to block inside a synchronized method. So many people don't know how to use JFR, and so this is sort of the getting you started kind of slide here. Shows you how to actually run something that actually captures a recording, and once you have a recording, you can use the JFR command line tool with the print command to be able to actually print out the what's called the virtual thread pinned event, and you actually get a stack trace that you actually see where the thread is coming from. So this is actually quite useful for seeing what's going on and why you might have pinning issues. We have expanded all of this with Jet 491 to add a bunch of new places where this can actually be recorded. So this has improved the diagnosability of pinning issues going forward, particularly when you start using FFM and JNI and native frames. These kind of things are actually going to be very, very useful. The other thing that we've added in JDK 24 is we've added a monitoring and management interface for the virtual thread scheduler. This allows tooling JMX-based tooling to get an insight into what is going on with the scheduler. So you can actually see how many virtual threads are actually mounted, what's my target parallelism. I can actually dynamically change the parallelism. There's people doing experiments on containers where they're dynamically changing the parallelism, and that's actually cool things that you can actually do with this. And there's a whole bunch of other serviceability things that I won't get into today. Is that we had the debugger and all the JVM TI tool interface working when in JDK 21. That has improved over time. We've a number of performance issues and bugs with JVM TI. They've gradually been worked out, and I think we're in actually much better shape on this. Heap dumps are really, really important for diagnosability. We didn't have all of the virtual threads in the heap dump in JDK 21. That has finally been addressed in JDK 23. So we actually have thread stacks of unmounted virtual threads now in the heap dumps. So you can actually do an analysis of heap dumps, and it's very, very useful to get that done. We have some prototype J commands, new commands that we've been working on in the Loom repo. They're in the early access builds. We haven't actually decided what or when to bring these into our proposal for the mainline. But there's a lot of information that we can dump for debugging purposes, including information about the schedulers, timers, the I/O mechanism, because all of this we actually can dump information about. So this is actually very, very useful to have for diagnosability purposes. And as I say, is over time we're going to build up more of this. I think the highest priority one that we have to get working is including lock information in the new thread dump. And there's particular technical reasons why that's not included, but we know where to go on this. It's just a matter of engineering work to improve on that. So that's all I'm going to say for diagnosability for the moment. The main take from that is that there's a bunch of features that are there in 21. There's a lot more features have been added since then, and more things are coming. Okay, I want to move on and talk a bit about structured concurrency. So structured concurrency is something that we've been tinkering with and playing with for a long time, actually more than 5 years on this topic. So I wanted to actually spend a little bit of time talking about what this is about. So for this topic, and for some people I know you've seen this before, maybe some people haven't. The motivating example I'm actually going to use to introduce this topic is I'm going to talk about something that is actually going to combine the data from some web service over here and some database over here. So it's going to fetch the two of these things together and aggregate the result of both. So I'm keeping it very, very simple. Okay, so I'm going to start with the sequential piece of code. This is boring code. And everything in Project Loom, when you're looking at the code, think boring, synchronous code. Everyone in this room can actually read this code. It fetches a user. Assume that comes from a web service. Fetch order. Assume that comes from a database. And then I'm going to combine them together. Now, what's interesting about this is when you start thinking about how would I use this in a debugger? It's going to work the way I expect it to do. I can single step. I can actually step into the fetch user and the fetch order method. I can actually see the code. If I were to take it, if something were to fail and I get a stack trace, I can actually see where it failed. If one of these methods were to hang, I can take a thread dump and actually can see where it actually hangs. So I have good insight into what this piece of code is actually doing. So let me just quickly run through what happens when I execute this. So because it's sequential code, I'm going to execute the first method, fetch user, which goes off into the cloud, fetches something from remote service that succeeds. Then I'm going to go off and do fetch in the something from a database that's also going to succeed. And then I'm going to combine the result. Very, very simple. Now, this is the best scenario. Both of those operations succeeded. But what if one of them were to fail? So let's talk quickly through this as we do some of the setup before we get to structured concurrency. So start again. Let's suppose that our fetch user method were to fail. And in this case, it's fairly dumb. It failed with an arithmetic exception. Okay, who cares what the exception is? The important thing is the stack trace is telling me where it actually failed. That's actually very, very useful. If it were to hang, as I said, in fetch user, I could see where it's actually hanging. So all good. Same thing if the fetch order method were to fail. I'm stepping through this, or I'm looking at a log file, I'm seeing an exception here where it actually failed. This is all very, very easy and very easy to understand. Okay, the thing about this example, or that last example, is I'm doing two different things. There's no dependency between them. I'm trying to aggregate the result, but it's slow. It's slow because I'm actually doing things sequentially. What if I want to make that overall operation faster by making it concurrent? And this is where it gets kind of interesting. Because once I start making it concurrent, then the world gets a lot more complicated. So for this example, I'm going to use a thread pool. It's just, I'm going to make some of this code disappear so the slide is left busy in a second. But if you look down at the bottom, private static final executor service pool equals executors.new fixed thread pool. That's creating my thread pool. That's essentially a pool of threads that I'm going to use to execute tasks. All right, so we're going to run through this a couple of times, and I've got the take one, take two, take three as we run through this code to see what's actually happening. So this code is using the executor service submit method. What that does is I'm giving it a callable that will run it on one of the threads in the thread pool, and what it returns me is a promise in the form of a future that I can actually use to wait on the result. So in this first take, I've done my two submits. So what's that done is it's taken those two tasks. They're now going to executing on the threads in the thread pool. Because these are running asynchronously, I have to wait for the results. So I'm going to call the future get method twice in order to get the result. First on the first task to get the result from fetch user, and secondly I'm going to call get on the future for the second task, which is running fetch order. So I have two gets that I'm going to have to block on. And so let's run this and see what happens. So first task succeeds. This is great. What that means is that future get, which is my main thread waiting for the first task to complete, that wakes up and I move on and I start waiting for the second task. And we will assume that that succeeds and we're all good. Sorry, I went too quickly there. That succeeds, we're all good. So we blocked twice, everything's fine. And with the concurrent code it's usually okay when things are working, because you're not having to diagnose problems. Yes, it's a little bit awkward when you're working in the debugger, because if I'm stepping through this, it's actually executing a different thread than I'm waiting on. So you've got a bit of confusion and you're trying to find out which thread I actually have to debug. But okay, that's just the way the asynchronous code kind of works. Okay, let's go through this a second time, and we're going to get something to fail, and let's see how this works. So this time, I'm here waiting on the first task to complete with future get, and the first task fails. So fetch user fails with some exception. That caused the task to complete. Task1.get, which is me calling the future get method, that's going to wake up and it's going to throw an exception. So I'm going to throw the exception from, in this case, it's an execution exception with the cause, which is the arithmetic exception, and that is because just the way the future wraps the original cause. But the interesting thing here is that the thread that's executing fetch order is still running in the background. I've got a leak here. This thing might consume this thread in the pool for a certain amount of time. This is a little bit annoying. So my method here is failing with an exception, but I've gone and left a task running on the thread pool. So this isn't great. So let's go and run this again. We'll get the other task to fail this time. So remember, I'm blocked waiting for the first task to complete. And while I'm waiting for the first task complete, the second task went and failed. And I'm still waiting for the first task to complete. So I'm kind of hanging around waiting for the first task, whereas I'm going to throw away the result of that first task in a minute. And then first task completes. We move on then to go and get the result from the second task, and I get my exception. Now the good thing with this is there is no leak here. it just happens the ordering that that I waited for the results matched the order, and it's okay. I didn't leak anything. However, I wasted cycles waiting for the first task to complete when I should really have been short-circuited or somehow being interrupted, or something should have caused me to wake up and not have to wait for the first task because the second task failed. So that's one of the annoying things of trying to do this with do these things concurrently. So you can fix some of these. I had a whole slide deck on all sorts of combinations of ways that people can actually fix this, and it ends up being complicated code, contorted code, hard to debug, hard to read. You don't want to do that. In general, and I know Brian is here somewhere, but he's got a whole section in his book on cancellation and shutdown that this presentation is here to address. It's a hard problem when you're using thread pools in the way I was using them there. So this is where we get into structured concurrency. It's one of the motivations that actually started us looking into structured concurrency. So at a high level, what it's about is it's really about simplifying these cases like I showed you here, where you've got a main task that splits into several subtasks, and you want all those subtasks to be done before the main task actually continues. It's deeper than that in that it actually preserves the relationship between the tasks and its subtasks. It supports actually abstraction. If I go and refactor some sequential method to be concurrent and have it fork off a whole bunch of subtasks, when that method completes, you want all those subtasks to be gone. So it actually preserves all of that relationship and gives you better abstraction there. It's very, very buggy to be working in this area of cancellation and shutdown. We don't want people to have to go and deal with all of the subtle bugs that you get with this. And the interesting thing is, turns out to be a wonderful match for virtual threads, because they're so cheap to be able to actually decompose, or to be able to create virtual threads to go and execute these tasks. So it actually works really, really well for these examples like I'm showing you here. If I were to show structured concurrency like just in one slide or one line, it would be like this. When a main task splits into several concurrent subtasks, then the subtasks must complete before the main task continues. Now, by the way, this idea of structured concurrency has been around forever. There's actually a book that we found that goes right back to the early 1970s on computer system organization, where this concept was actually shown, but it used a completely different name. The name structured concurrency is something that Martin Sustrix coined, I think around 2016. He was working on something to do with some library in the area of embeddable network libraries, and he coined this phrase for the type of architecture that he was coming up with. And so it's kind of stuck, and then it became known, got well known within the Java ecosystem when a guy that was working on Python's Trio library at the time, a guy Nathaniel J. Smith, wrote an article on it. It became widely read in the Java ecosystem, and that's where the term, I think, got introduced to the Java ecosystem. There's a lot of other things that have influenced structured concurrency, things like Erlang's hierarchical supervisors are another way of thinking about structured concurrency as well. But anyway, let's move on and talk a bit about what we have. So this is something we've been toying with for a long time. We had prototype APIs around this going back to 2018 or so. Some of the naming and some of the APIs were pretty terrible at the time, but they always are in first iterations of APIs. But we knew that there was something interesting there that we had to keep on iterating on and try to find something that would be good to expose. So what we have been focused on is trying to expose something that is a very basic API, something to actually to get you started, at least an on-ramp towards structured concurrency. And the idea would be to try to encourage kind of a use here that would avoid some of the bugs that you would run into if you attempted to do the shutdown and cancellation and clean up that you would get without this kind of an API. I'm quite confident that the API that we will eventually make permanent, assuming we make it permanent, is not the last word on this topic. It's not the definitive API. There will be many other structured concurrency APIs of different shapes and forms, but they will employ similar kind of concepts. But I think what we have And what we've been playing with is something that gets people started with the concepts and introduces them for use to regular developers. Okay, so let me show you the API that we actually have here. So this is what we have in JDK 21. And this is a preview feature in JDK 21, preview feature in 22 and 23 as well. So this API is called Structured TaskScope. It lives in Java Util Concurrent. It's an API that's designed to be used with the try with resources construct. So you've actually you kind of visualize this as sort of a syntactic block. You create one of these in the try, and it gets closed then when you're done. You get one of these structured task scopes, and it only defines a tiny number of methods. It defines methods for forking subtasks, and it defines you a method to do a join. So in the example that I'm actually showing you here is exactly the example that we had with the concurrent example a couple of slides back. So I'm creating one of these things. By the way, I'm creating something here called a shutdown on failure. I'll explain that in a second. But what we're doing is forking two subtasks, our fetch order, our fetch user, and our fetch order, exactly as we did before. But we're only joining once. In the previous current examples, we were waiting on future twice. You do not wait on subtasks with this API. There is just one join. I'm only waiting once. There's one barrier. And then once I get through the join, I'm able to combine the results of the two subtasks. So that is kind of how this thing works. The important thing that it ensures is that when you close a structured task scope, there will be no threads left behind. There are no subtasks left behind. Every time you create one of these subtasks, it will start a virtual thread to execute that subtask. That actually makes it very, very cheap, at least when you use the defaults. Now, I said this was called shutdown and failure. The reason for this is a structured task scope that implements a policy that basically shuts down the structured task scope when any of the subtasks fails. This is what the API is in JDK 21. What we have in our Loom early access builds is an improvement to this API that we hope to make preview in the next release. And what the improved API is it basically it avoids using constructors. So here's the existing API. Here's the API that we actually have in our early access builds that we hope to propose for the next preview. So instead of using a constructor to create a shutdown on failure, I'm actually using a static factory method called open that does the same thing. One other slight change in this one, I'll go back. Oops, there's the existing API. You'll see scope.join.throw failure. This is actually where we actually have to opt in to propagate exceptions from subtasks. That's a little bit of a wart in the old API. It's a hazard that a number of people have actually pointed out. So we've been trying to actually smooth that down by having the join method actually throw. So with the improved API, we get this. So the structure of the API is the same. We've got try with resources. We create a structured task scope with the static factory open method. This gives us back a scope that we can actually use to fork subtasks. Each one of the subtasks will actually create a virtual thread to execute it. And then we've got a single join method. And when that join method completes, I can call subtask get and get the results of the subtask. I'll go through some examples of this quickly. This is actually a really, really simple API. Okay, I'm going to go through a couple of the scenarios again where things pass and where things fail, because that's the world we live in. So, color coding. The blue circle is the platform thread. It's the main thread that's actually executing this thing. When I show little orangey threads, there are virtual threads, and you will see some of these as we go along. Okay, so let's walk through this, how this would actually work. So, red little arrow here, kind of think of it as the program counter on a slide. So we get to the first statement here where we're actually going to do scope fork, and we fork a subtask to execute fetch user. What does that do? It creates a virtual thread to execute that subtask. Conceptually, think of this as a child of the current thread. I get to the next fork, and I create another, I do fork again to execute a second subtask. Now I've got 2 children, both running in their own virtual threads. Then I do a join. I'm now waiting for these two subtasks to complete. First task subtask completes, virtual thread terminates. Second subtask completes, virtual thread terminates. Now the join wakes up, and I'm able to actually deal with the results and aggregate them into this result record that I've got here. Very, very simple. Now let's run it again. Assume we've actually forked our 2 children, and something is going to go wrong this time. It always does in take 2. This time, the first subtask is going to fail. The thread executing that first subtask terminates with an exception. What happens next? The second subtask is cancelled. Cancelled here, just think thread interrupt. And when the main task here gets to the close method, it throws an exception, a failed exception, with the exception of the subtask as the cause. What's interesting here is that the main task is only going to continue when all of its children have actually terminated. I've attempted to interrupt or cancel all the threads that are executing the subtasks, and only when these stragglers have actually completed will the main task complete. So that addresses the cancellation and avoids then leaving anything behind when the main task continues. Do it again, this time take 3. I've got my 2 children. I'm waiting for them both just to complete. Second subtask fails. In this case, what happens? First subtask gets cancelled. Main task then throws the exception with the exception from the subtask as the cause. Very, very simple. So there's our three scenarios. But what it gets more interesting in that I'm now going to go and I'm going to actually refactor one of these methods. I'm actually going to refactor both of these methods, the fetch user and the fetch order, to create their own subtasks, or their own structured subtasks. So main task has 2 children. Fetch user will have 2 children. Fetch order will have 2 children. And behold, a tree. So here I am in the main task, waiting for my 2 subtasks. Those 2 subtasks are then waiting for their own children. So we have a little tree of subtasks. Now, in any of the real-world applications we've tried out, this tree tends to be quite shallow. It's not a very deep tree, but it's still a tree nonetheless. So it's actually quite interesting. Now let us see what happens when something fails in this tree. So one of the subtasks that fetch user forked failed. What's going to happen? Well, that scope is going to cause any of the other subtasks in that scope to be cancelled. It's going to fail, and then that is going to cause the parent who's waiting for its subtasks to deal with a failure from one of its subtasks. It's then going to cancel the subtask on the other side, and that propagates then down through the tree. So what you end up doing here is actually cancelling a tree of subtasks, which ends up actually interrupting all of the threads that are actually executing those subtasks. And this is actually very, very simple. It just happens. And then the exception that I actually get is actually giving me some information about the tree as well. Maybe it's probably hard to read this on the slide. I'm waiting in the main subtask, or the main task. It's throwing a failed exception. I'm seeing the cause as from the subtask that failed. In return, its cause is the cause from its subtask. So you're actually seeing a little tree of causes as well. So this is how this works. So everything so far has been the join method is basically waiting until all of the subtasks succeed or one of the subtasks fails. This is something where we get into the concepts of policy and outcome. Shutdown and failure is what implemented this policy in the old API. In the new API, we have this notion of a joiner. And this is how we actually implement different types of policy and outcome. And you can provide one of these objects to the open method to get other type of policy. Conceptually, just think of it basically as a concurrent mapping of the results from subtasks to some result that join can return, or some exception that join can return. That's the way it actually works. Here's a quick example of it using a different policy. This one here is implementing a policy where I'm doing a race. Basically, whichever subtask completes with a result first, I'm going to use that result, the other gets cancelled. This is how it looks in this API. Here's another one of the joiners that is actually built in, which is for dealing with subtasks that return results of the same type. It implements the same policy as what we have seen already, but what it returns is a stream of the successful subtasks. So you can actually use it in a street pipeline to in this case, in this example, it uses the map operation and returns everything in a list. So very, very simple. And you can build your own joiners to do all sorts of other interesting things. So wrap up on structured TaskScope is very, very basic API, but a very, very powerful API. Remember the goals, have something that's an on-ramp, simple introduction to structured concurrency. And we're hoping that this API that I've shown you here will actually be the next preview in JDK 24. But it's really important that we actually get more feedback and more people using this. One of the things about introducing virtual threads is that everyone has jumped on this. They haven't actually consumed this elephant yet and moved on to the next thing, which is structured concurrency. Right, and here we are done. So summary of the next steps is that at least for the next while, our focus is on addressing the issues with object monitors, expanding all of the diagnosability features because we're going to have a lot more virtual threads in production, and then we're going to have 2 more preview JEPs for 24, one for scope values. I didn't talk about scope values today. That's already submitted, JEP 487, and then we have a new JEP for structured concurrency. And that's it. There's the links. So this is the last session of the day, and it means that I get an unbounded session. So happy to take questions, and I think I'm okay to take sessions here. Yeah, I got a nod from the AV person that if people want to just keep asking questions, I'll deal with it here, even though our time is up. Okay, I see a hand already.
How does structured concurrency work with our current async stuff like futures?
Okay, sorry, did you say fusion or futures?
Futures.
Okay, so structured concurrency does not use futures. We actually have a big section in the JEP as to why we don't use futures. The big thing with future is that there's a method in there called future get. And it's too tempting to call future get. We had experiments, we went through many, many iterations. We were actually returning futures at one point. And the thing, as soon as you start introducing futures, the first thing people want to do is call future get, whereas what you want them to do is actually call the join method and wait for all of the subtasks to complete, not wait for individual subtasks. So that's why that's not in that API.
But there are many libraries or whatever that return futures, and that's what
Okay, right. So the question is about a lot of existing libraries actually return futures. So this is going to be incompatible with these, and that is correct. Yes, we have a big write-up of this in JEP 480 if you want to just to see why we moved away from future. Okay, so there's several hands. I'm trying to see, I don't know what the ordering is. Maybe you up there first, Nick. Yeah.
Sometimes the cancellation model is considered a bit easy to misuse in Java. Would you agree with that? And are there plans to revisit this a little bit?
Okay, so the question is about the cancellation model in Java can be hard to use, and are we revisiting this? Okay, so we spent quite a bit of time prototyping alternative cancellation mechanisms, including level triggered models, which is much more higher level than the lower level sort of thread interrupt mechanism that we have today. We worked out all of the mappings between the two, but we didn't come to a conclusion that it was the right thing to do to expose something else. It is so confusing to have 2 different models for cancellation, and so it's one of these worse is better. We continued with the existing thread interrupt. Okay.
You mentioned prior signs comes to structured concurrency from the 70s, which was that?
Oh, we get out the Burroughs book. Hang on. Let me go and find this. We had to. Let me go and find this. Where was this? Okay. Right, so the book was 1973, Computer System Organization by Elliot Organic. And you can actually find it online.
Yeah, thank you. Thank you.
It was not called Structured Concurrency, though, at the time. And credit to Andrew Haley for digging up some of the old history on this. Sorry.
What is the best way of integrating virtual threads with parallel streams, such if your stream operation has some blocking operation?
Okay, so the question is about parallel streams and blocking operations. Have a look at the new Gatherers API, map concurrent. That's the API you want.
Yeah, so with all those changes that came up with concurrency in the last 18 years, usually when a junior developer comes to us, we address him to read the concurrency practice book and then forget half of it and add the rest. Can we expect a new edition? Brian was here a couple of minutes ago, but sadly he left.
Brian put on his coat. Sorry, so the question is about concurrency in practice and whether there'd be an update to that book. Brian has been talking about doing this for years. I don't know. He headed out a few minutes ago. Sorry. There's definitely enough material to revisit that book in 2024. Okay. Okay. So, question.
When switching to virtual threads, one of the biggest problems we had was that the systems behind it couldn't follow with the new, the load we can put on those. Is there any ideas for throttling? Because we had to revert back to just a thread pool because the backend system.
Okay, so the question is about you've refactored something to use virtual threads, but it ends up there's no throttling in there, so you end up overloading some other part of the system. So with traditional thread pools, is your size of your thread pool end up being your throttle. That's actually determined your concurrency. Moving to virtual threads means that you're controlling or wanting to limit concurrency at a much finer level of granularity. And this is where you have to use some other kind of construct, essentially semaphore type semantics, to be able to limit concurrency at the right level, whether that would be a limit on the connection pool to a database or something else. It'll be something at a much finer level of granularity rather than threads.
Could that be something that lives in structured TaskScope?
Okay, so question comment is whether this could live in structured TaskScope. This is something that we have explored. I don't know where Victor is. Victor didn't make it here, did he? No, Victor Klang and I've been working on this API, and we haven't come to agreement as to whether this is the right thing to do or not, because it's not necessarily threads. It's more specific to the domain where you actually might want to limit things. Okay, Mario.
If I understand correctly, if one of the asynchronous call throws an exception, it's supposed to be an error. So when you do join, one of the things throw an exception, and that is the signal that something went wrong, and you cancel all the other thread, right? But in some cases, you are using exception for simple control flow. In this case, I mean.
Okay, so
A way to not throw an exception, return a value, but that value to me is an error, and I want to cancel everything.
all right, great question. So this is about subtasks that complete with an exception. There may be cases where you don't want to treat this exception. You want to maybe map it. It's using exceptions for control flow, mapping to a default value, something like that. And this is where using your own custom policy or custom joiner in the new API allows you to do other things. You don't have to a subtask failing doesn't have to cause join to fail. You can actually map that exception to something else. So that's actually easy to do. Sometimes for default values, it may be that this is actually handled in the subtask itself. So rather than the subtask failing with an exception, it catches the exception and returns some default value in that case. That's an alternative way of doing this.
Is the joiner API available in 24 early access?
Okay, so the question is the joiner API in 24? It's in the Loom early access builds. So we have drafted a JEP, we just haven't, it's not on the technical roadmap yet to refresh the API. So it's not in the JDK 24 early access build, it's in the Loom early access builds. Okay, so question up here.
About scoped values, they are not inherited except with structured concurrency. What is your advice for use cases like log contexts or distributed tracing to get certain identifiers to virtual threads?
Right. So this is a question about scope values, and using scope values to be able to for things like logging contexts, where you call something, set some local, and you want it to persist after that method completes. That's just not a good use case for scope values. Scope values are very much about being they can only replace a subset of the usages of thread locals today. It doesn't replace all of them. It's very much about having scenarios where you execute some particular piece of code with a scope value bound to some value. I think the mental model to get into with scope values is just think of it as an implicit parameter. It's like there's an invisible parameter through all of the methods to some faraway callee. That's the best kind of mental model, I think. And once you get that into your head, these logging context things that want to call them, set some value, and have it sit on the be tied to the thread after that method completes, those kind of ideas disappear.
Sorry, we have to wrap up.
We have to wrap up here. Okay, so I'll be outside if we want to take more questions. And so thanks very much for coming along.
All systems are nominal. Initialize Genesis sequence.